This video is going to be about pulleys. Pulleys is basically going to be a continuation of what we've already done in terms of systems. But to do that, we need to view pulleys in a special way. Okay, so basically what we're going to cover is how to describe a pulley system and the process of converting a pulley system into a regular system, and then how do we calculate the various forces and the accelerations associated with pulleys. Okay, first off, what a pulley does in a system is it changes the direction of the forces. In the example given here, M2, the force on M2 is downwards, yet the force on M1 is sideways. So what the pulley did here was it converted the force of M2 into the downward force of M2 into the horizontal force of M1. And if we can undo that process, we can effectively think of pulleys as simply two masses connected by a string, similar to what we've done in terms of systems. Okay, so this is the free body diagram that we would draw. We'll assume that there is some amount of friction on M1, though that doesn't have to be, as we'll see on the next slide. We're going to be ignoring several forces. In particular, we're not going to look at the forces on M1 that are in the vertical, because the force of gravity on M1 and the normal force on M1 effectively cancel out. What we're also not going to look at in this free body diagram is the tension force on M1 and the tension force on M2. Those two forces are internal to our system, so we're not really going to pay any attention to them. But what we do need to do is we need to remove the pulley from the system and straighten out our two-body system into a single dimension, okay, just a one dimension. So let's get rid of the pulley, and then we'll rotate M2 so that everything basically is in one dimension. Okay, force of friction is to the left, force of gravity on M2G now is to the right. Okay, so I can now combine those two masses, M1 and M2, and there are two forces, one to the right and one to the left. And this is a very simple problem where if I wanted to calculate the acceleration, I can do that with M2G being a force on one side, friction on the other side, so it'll be negative, over the total mass of M1 plus M2. Okay, so here's the same system, and when we do that, we find that if there's no friction, I really only have one force acting on this to make my system go. Okay, the force of gravity on M2. There's no friction on M1, so I don't need to worry about that. In that case, my acceleration ends up looking like this, M2G over M1 plus M2. With friction, we get the formula that we saw on the previous slide. Okay, so at home, I'd recommend doing some of this practice in terms of drawing these pictures straight. Okay, we can talk about this in class when we meet next class. Okay. Here's an example with numbers, okay? I have a 5 kilogram mass that is hanging off the table while a 3 kilogram mass is on the table. And again, they're connected by a string over a pulley. We'll ignore friction, find the acceleration in this case. Well, we've already found the formula for this, okay? It's just the force of gravity on M2 over the total mass of 8 kilograms in this case. So plugging in these numbers into our calculator, we find that the acceleration of both objects, M2 downwards, M1 to the right, is 6.13 meters per second squared. Part 2 of this problem will always be pretty much to find the tension. We could go backwards and find the tension first and then acceleration, which we'll do in a couple of slides. Okay, but right now, since we know what our acceleration is, we can look specifically at just M1. Okay, we could pick either M1 or M2, but M1's a little bit easier because tension is the only force making M1 move to the right, especially since friction doesn't apply in this example. So if M1 accelerates at 6.13 and tension is my only force, I divide by the 3 kilograms of my mass and solve for the tension. Tension in this case is 18.4 newtons. I could have done the tension on M2 drawing the free body diagram, and again, if I had gotten everything correct, yes, my tension would also be 18.4 newtons. Okay. The other way that we can solve pulleys or any kind of system is to treat each object separately. To do that, we would draw the free body diagrams and write the Newton's second law equation for both objects. So here's the free body diagram for M1 in this example, okay? Gravity downwards, tension up. Because we're treating each object as separately, we do have to include those internal forces of tension. I'm going to make an assumption here that acceleration is down on M1. If the acceleration is down on M1, then acceleration must be up on M2. It's important that we are consistent, okay? It has to go one direction or the other. In this case, I'm simply making the assumption that M1 is down. It's okay that I can assume that because when I go through the calculations, if my acceleration turns out to be negative, I'd simply flip the directions, and as with all negative vectors, flipping them will make them positive. So now that I've drawn my free body diagram, I need to worry about writing my Newton's second law equation. So here's the Newton's second law equation. Tension up, positive, force of gravity down, negative, and minus m1a. It's important that you draw the direction of acceleration and pay attention to that minus sign there. Acceleration is downwards, so my m1a must also be negative. Let's solve that for tension, and we find that tension is equal to m1g minus m1a. The reason I'm going to solve it for tension is because I'm going to need it in the next equation. Okay, so Newton's second law for the second object, here we are, tension again is equal to m2a plus m2g now. Okay, now that I have the two tensions and the two tensions must be the same as well as the two accelerations, I can solve by setting them equal to each other. Okay, so instead of tension equals those two equations, I'll set those two equations equal to each other. I'll group all my accelerations to one side, factor, and divide. Okay, and in this case, my acceleration for this system is going to be m1 minus m2 over m1 plus m2 times g. Notice in both of these examples that my acceleration will always be less than or equal to g, some fraction times g, and that fraction must be less than, or in some rare cases it would actually be equal to 1, but most of the time not. Okay, so that's kind of a hint that if you ever get a number greater than g, 9.8, you're probably on the wrong track and you need to go back and double check your calculations. In particular, my suggestion, check out all those minus signs. Okay, thank you.